Welcome back to part 2 of Module 5, Lesson 2, dealing with real numbers, and we're starting off with Example 2, Classify Real Numbers. And the question is, name all sets of numbers to which the real number 0.2525 and so on. We call these things right here, those are called ellipses. And what ellipses mean is that this pattern is going to go on and on forever. 25, 25, 25, 25, and so on throughout all time and eternity. It's never going to stop. So let's find out what all categories that number is going to fall into. The set of real numbers include natural numbers, whole numbers, integers, rational numbers, and irrational numbers. So, first off, can you express this in the form a over b, where a and b are integers? Well, is it a repeating decimal? Yes, it is. And since it's a repeating decimal, the answer is yes. And that number would be 25 over 99. I'm sure you knew that right off the top of your head, didn't you? So since it's a repeating decimal, repeating decimals are rational. Therefore, they can be written as a fraction. Next, is the number from the set of integers that goes from the negatives all the way to the positives? Well, it's not an integer. Integers are 1, 2, 3, negative 1, negative 2, negative 3. That's a decimal value, so the answer is no. We have now said that it is rational, but it's not an integer. Let's keep going. And that's the home button, so that's the end of that one. Now it's going to be your turn. Select all that apply. To which sets does negative 2 and 2/5 belong? Well, it exists on the number line, therefore we know it's going to be real, but a real number is not there. It is a fraction. Now it's a mixed number, but we could make it into an improper fraction, and since it's a fraction, it's going to be rational. If it's rational, it's not going to be irrational. You can't have both. It's not an integer. Integers are 1, 2, 3, and their opposites, and of course 0. It's also not a whole number, 1, 2, 3, and it certainly is not a natural number, because if the caveman tried to couple up with negative 2 and 2/5 sheep, that would be kind of messy. It'd also be a negative number, so it really wouldn't even be sheep at all. I guess that was the aftermath of eating 2 and 2/5 sheep. Like I said, kind of messy. The only correct answer here is going to be A. It's going to be a rational number. How about the square root of 36? Well, the square root of 36 is, what number times itself is 36? 6. Good. So and we can ask ourselves, can 36, therefore, square root of 36 be written as a ratio in the form of a over b, where a and b is integers and b is not equal to 0? Absolutely. That would just be 6, also known as 6 over 1. That means that it is going to be a rational number. The next question is it in the form of integers? Well, yeah, it falls in 1, 2, 3, and after that you got the ellipsis 4, 5, 6. So yes, indeed, again, it is going to be an integer. Let's keep going from here. Is it going to be a whole number? Absolutely, because a whole number is going to be the positive integers and 0. So yes, again, it is going to be a whole number. Take it further. Is it a natural number? Can caveman own 6 sheep? He absolutely can own 6 sheep, although I don't think he'd have any idea that it would be the square root of 36. So once again, the answer is yes. So we have lots of different things that the number 6 actually belongs to. Can you say your turn? Tell me what the square root of 100 belongs to. Did you do it? Did you get them right? Well, the square root of 100 is 10, because 10 times 10 is 100. 10 is a whole number, it's a terminating decimal, so it's going to be rational. It's going to be an integer. It's going to be a whole number. An old caveman, he'd be real happy to have 10 sheep. Therefore, it got all those. The only thing that the square root of 100 was not is irrational. Now, how about the negative square root of 7? Well, it's not imaginary, because that negative sign, it's outside of the radical sign. The square root of 7, though, that I'm pretty sure is going to be an irrational number. Let's see what they show us. And they would say, well, here it is right here. Yep, that's looking pretty dang irrational to me. It is a non-terminating, non-repeating decimal. So the answer is no. Therefore, it is going to be an irrational number. Can it be written as a ratio of a over b, where a and b are integers and b is not equal to 0? Answer is no again. Once again, it is an irrational number. Easy math. Anybody can do this stuff. If it's irrational, you don't have to worry about all those others because it can't be them. It can only be those others if it's a rational number. If it's an irrational number, it is just irrational and nobody wants to hang out with it because it is behaving so poorly. So how about the square root of 10? That's a positive 10 there. Give you a leg up here. I'm going to go ahead and break out the calculator on this one for you just to help you out. 10 square root. What y'all think? A lot of numbers there. I don't see a pattern to it. Non-terminating, non-repeating decimal. Therefore, the only thing it can be is irrational. Once it's irrational, all of its friends ran off and left it because no one likes hanging out with irrational people. We are closing in on the finish line here. Some sets of numbers are subsets of other sets of numbers. For example, rational numbers and irrational numbers all belong to the real number system. Now we're going to watch a video about how to use the Venn diagram to categorize different types of numbers. I think we've already talked about this some.
The set of natural numbers includes the counting numbers 1, 2, 3, 4, and so on. Natural numbers are a subset of whole numbers. The set of whole numbers includes the natural numbers plus 0, so all natural numbers are whole numbers. Whole numbers are a subset of integers. The set of integers includes the whole numbers plus their opposites and 0. All whole numbers are integers. Integers are a subset of rational numbers. A rational number is any number that can be written as the ratio of two integers where the denominator is not 0. All integers are rational numbers. An irrational number is any number that cannot be written as the ratio of two integers where the denominator is not 0. Rational numbers and irrational numbers are subsets of real numbers. All rational numbers are real numbers, and all irrational numbers are real numbers.
That kind of begs the question, what is not going to be a real number? Well, we've already talked about that. The square root of a negative number is an imaginary number, and since it's an imaginary number, it's not going to be a real number. Now I'm going to take a little screenshot of this because I think it might come in handy here in just a minute, and we're going to keep right on moving with our lesson. The lesson continues to say, if a given statement about a real number is false, you can provide a counterexample. A counterexample is a statement that shows a conjecture is also false. So that's going to be a goal here to figure out, can we create a counterexample, something that will show how it is going to be false. So let's use a Venn diagram to determine whether the statement is true or false. If the statement is true, we're going to explain our reasoning. If the statement is false, we're going to provide a counterexample. All rational numbers are integers is going to be the first one. Well, rational numbers encompass the entire rectangle here, and you can see that you've got natural numbers and whole numbers and integers there. And so, yes, all of these are rational numbers, but what about the 0.3 repeating over here? That's a rational number too, and it's not going to fall into the integers category. So we can take and say integers are subsets of rational numbers. Therefore, the statement is false because looking at that Venn diagram, if it had been the other way around, if we had, let me pull this up over here so you can see it. If we had it said that all integers are rational numbers, that would have been absolutely true. But because it was the other way around, all rational numbers are integers, that one is absolutely false. Let's keep moving. To provide a counterexample, One possible counterexample would be 0.6. That is a decimal value that's a terminating decimal. It is not going to be an integer, and that is a proof that not all rational numbers are integers. 0.6 is a rational number, but 0.6 is not an integer. Now it's going to be your turn to figure out whether or not this is a true statement, and if it is not a true statement, you're going to have to provide yourself with a counterexample to explain why not. All integers are real irrational numbers. What do you think? Looking at my Venn diagram, integers are over here. Irrational numbers, remember, they're in their own space. They're sad, lonely little people because they behave irrationally all the time and nobody wants to hang out with them. Not smart to behave irrationally all the time. So the answer is false, that not all integers are rational numbers. Check our answer. That checks, and then we could take and type a counterexample and say, well, what's an example of an integer that's not irrational? And that would end up being 1. 1 is a terminating decimal. It can be written as a fraction. It is a totally rational number that is not irrational. And you could type something like that in right here. Well, I had a little internet trouble, but it's back now, so let's keep going. Here's our next set of numbers here. Do that one on your own. All irrational numbers are real numbers. Well, what do you think? The answer is, yep, that's going to be, that's the wrong way. The answer is, yep, that's going to be true because irrational numbers fall in the real number category. They are on the number line, so it's going to be a true statement. And our last problem, because even if there's an apply, I don't want to do it. I'm done for the night. We want to look at, are all integers real numbers? Well, let's see here. Integers are right here, and our till, they fall under the big umbrella of real numbers right here. So once again, the answer is going to be, let's see here. The answer is going to be true. We're going to check that and then explain your answer or provide a counterexample. Well, there's no reason to provide a counterexample because it's true, and I already explained it to you when I went over it. Exit ticket? Nope, we're not exiting. We are exiting now. So y'all have a great day. Get busy on your homework. I don't think it'll take you too long if you truly understand your definitions. I'll see you tomorrow.